Okay, so this is 4.4, video 2. We're going to run through some examples of the net change theorem and the importance and the application of those. So again, I've pulled some problems that were from, at this point, quite old AP exams, but I still think that they're good problems for us to run through. So the first one says, a particle travels with a velocity given as v of t equals quantity t minus 2 times sine of t meters per second from 0 to 4 seconds. We want to find the particle's displacement, and we want to find the total distance traveled. A couple of key things to this. First of all, this was on an old AP test. It is important to know that sometimes the setup of these problems is at least worth points. So just from the AP perspective, that's a good thing to know. So we know that a displacement is an integral of a velocity. No absolute value, just displacement, so it's just the integral of the velocity. So literally setting up the fact that we are going to integrate from 0 to 4 of v of t dt, sometimes that can get you some points, because that tells you that you know you're going to find the displacement. So here's the thing. You don't have to write the t minus 2 sine of t if it's defined as v of t. You can write the v of t. It's the same thing. And since what we're going to end up doing is using our calculator for this stuff anyway, there's no reason to put it to write the entire thing out, especially when you're going to get some much more complicated functions to deal with. Now, technically, this one can actually be done, this t minus 2 times sine of t. We just don't have a method for it yet. That's coming soon. But it can be done without a calculator. In this case, this was something which was on a calculator problem, so we're going to go ahead and just use the calculator anyway. And before I actually show you the calculator stuff, we're going to look at number 16, which says, what's the total distance? Total distance, again, the only difference there is that total distance is going to be the absolute value of velocity. So now knowing how to plug these things into the calculator is pretty important. So let's go ahead and pull up our handy dandy TI-84 calculator, and I'm going to show you some of the calculator steps that are going to be required here. So the first thing is, if you have a TI-83, you are not going to be able to do it in this exact fashion. I am going to try to show you how to do this both ways, but I'm going to rely more on the fact that most of us have TI-84s or some version of a TI-84. So the first thing we want to do is we want to plug the function into our y equals screen. So the fact that we don't have, I mean, we could technically use t's, but you may as well just use x's. There's no reason changing all that. So you're just going to type in x minus 2 and then sine of x. And don't forget, so I'm going to push enter here, don't forget to make sure that your calculator is in radian mode. We are in radian mode, so we're good. All right, so I've got that in my y equals screen. I want to graph this. Specifically, well, actually, we don't have to graph it, but I'm going to show you what happens when we do graph it. So I'm going to graph it on a standard 10 by 10 window, so that's a zoom 6. And we're only looking at 0 to 4. So, by the way, you would not do all these different steps. I'm going to show you a much, much shorter way in just a second. If you have the TI-84. Since you have the if you have a TI-83, this is kind of the way you have to do it. We only need to see from 0 to 4 seconds. So I'm going to change my window, push the window button, and I only need to see from 0. So x is going to go from 0 to 4. And then we're going to graph that and see what it looks like. A little hard to see there because it's so close to the x-axis, so I'm actually going to zoom this thing down a little bit. I'm going to change the window one more time. I'm not actually going to use the zoom button. I'm going to change the y max and min because I don't need to see that high up. So the y max I'm going to make, I don't know, no, sorry, the y min I'm going to make like -4. And maybe the y max +4. I don't think it went above and below that. Let's find out. Okay, perfect. So what you can see is I definitely have, this is kind of like the graph on the previous video, I definitely have space below and above the x-axis in this case. So when we take the displacement, it's going to take into account the area that's below as negative and the area that's above as positive, add those things up and get the total displacement, or how far the particle was from its starting position. And then when we do the absolute value one, it's actually going to change that so that all the area is positive. So let me show you graphically what this is going to look like. So if I was going to do the integral from 0 to 4 of this to show it graphically, I'm going to push, I believe it is second trace. And what you should see at number 7 is something that looks like an integral. It's exactly what it is. You should also, by the way, notice that number 6 is a derivative. Number 7 is an integral. Now the lower limit is 0 because that's what it tells us on the screen there. So we're going to type in 0, enter. The upper limit is 4, type in 4, enter. And lo and behold, it fills in all of the area and shades it, and we get our answer. Negative 1.449. Remember that you have to be accurate to 3 decimal places, so you can round or you can just write those first 3 decimal places exactly as is. Either way is acceptable. So negative 1.449, and then there's a 5 at the end. So negative 1.449. And let's see, that is going to be in meters. All right, what is the total distance traveled? Now we want to look at this thing. So let me pull the calculator back up as an absolute value. Again, normally we would not spend this much time, but since it's the first time seeing this in the calculator, I'm going to show it to you this way. Okay, get the calculator back. There we go. All right, so I'm going to go back to my y= screen. Show you a couple of different tricks. I could retype that entire thing as an absolute value. Probably a waste of time. What I can do is I can move down to the second y2, and there's a couple different ways to get to absolute value. I believe if you push math and then move over to num and the first thing is ABS, which is absolute value. You can also do it by pushing second 0, which is the catalog. It just so happens that ABS is the very first thing in the catalog, so you can get to it that way. Most of us are probably going to use the math button. It's just the one that we're used to, so let's quit this. So we'll go back to our graph, and then, oh, sorry, the y= screen, excuse me. Go down to y2. So we're going to do math, absolute value, and I want to take the absolute value of everything that's in y1. Again, instead of retyping everything, you can actually go to, if you do alpha trace, which is F4, it's going to pull up all your different y's. I'm going to select y1, and it's going to plug in y1 into the absolute value. So really, it's telling me I'm going to take the absolute value of everything I already have typed into y1. Now, I don't want both of those things to graph. I only want y2 to graph, because that's the absolute value function. So I'm going to scroll up to y1. I'm going to move over to the equal sign, and I'm going to push enter. It's going to unhighlight the equal sign. So now the only thing that it's going to graph is y2. And I haven't changed the window, so it should still graph the same thing. Now what we should see when we graph this is, because it's an absolute value, everything should now be in the positive area. So in other words, all the graph should be above the x-axis. Let's see. And there it is. It's doing exactly what we said it would. And then we can go back to the second trace to do our calculator functions and find the area between 0 and 4 under that curve. So that's going to be second trace, integral, which is 7, from lower limit 0, enter, to upper limit 4, enter, and it will graph it, shade it. There it is. And what we get is 1.9139. So again, you could round that 3 up to a 4, or we can just write 1.913. So equals 1.913 meters. So what this is saying is this particle traveled a total distance of 1.913 meters and ended up 1.449 meters to the left of where it started from, because that was the displacement. So that's what this is saying. All right. I know I've spent a lot of time on this one, and I'm probably going to do 3 separate videos. I'll do one for each one of these problems. I want to go back and show you now with the TI-84s. This is, by the way, that's the way you would do it if you had a TI-83. You'd have to graph it, and you'd have to do it by using the area. That's actually not true. There's a way to actually type it in. Syntax-wise, I really don't know it, so I'm not as comfortable with it. So I would use the graphing method that we just showed here if you have a TI-83. If you have the 84 plus Silver Edition or 84 plus Gold, whatever it is, as long as you have the upgraded operating system, this next thing is really cool. You can do this. So let's clear this out. Say I don't want to type all this stuff into my y equals screen. I can, I don't have to. I can do math, and if you go scroll down, I'm going to scroll down so you can see it. If you look at 8, it says n deriv. If you look at 9, it says fn int. Fn int means you're going to take the integral of a function. So if you push math and then 9, you can scroll down or just hit math 9. Wow, it's an actual integral symbol. That's so cool. So now I just have to fill the stuff in. It's 0 to 4. And let's just go ahead and do the displacement. It's an easier one to type in. So it'll be x minus 2 sine of x. And you do have to type in the fact that you're using x as your variable. And boom, there it is. Okay, if you wanted to type all that stuff into your y equals screen and then do the absolute value. So once again, that was all the stuff that was in y1. So I could do math 9. There's my integral, 0 to 4. Now I could do math num for absolute value. It'll insert the absolute value, and then I can do alpha f4. And I'm going to select y1. That was the original x minus 2 sine of x dx. I got to actually hit enter. Boom, there it is. So lots of cool calculator tricks. This is stuff that you will definitely want to familiarize yourself with. All right, let's move on. Same type of problem here in the fact that we're talking about particles. Particle moves along the y-axis this time, so now it's moving up and down. It's vertical. Not that that really makes any difference, but just to give you a sense of what it's doing. The velocity is given by t sine of t squared. It's not sine squared of t. It's sine of t squared. The angle itself is squared. For times greater than or equal to 0, in which direction, up or down, is the particle moving at time t equals 1.5, and why? Well, if we want to know the direction a particle is moving, you need to know the velocity, whether the velocity is positive or negative. If the velocity is positive, it's moving in the positive direction. If the velocity is negative, it's moving in the negative direction. Since we're talking about up and down, up is considered to be positive, down is considered to be negative. All we have to do is plug in 1.5 into our velocity function. So we'll do v of 1.5, and it is not necessary for you to show the calculations. You just plug the stuff into your calculator. So let's do that. So we're going to have 1.5 times the sine of 1.5 squared. And we're in radians, so we should be good. And that gives us a velocity of, 1.16, what was it, 7? And that would be, what was this in? It doesn't say, but I'm assuming this is probably meters per second or something like that. But if it doesn't say unit, you don't have to include them. But there's your velocity. The velocity is positive, so we would say v of 1.5 is greater than 0. Therefore, that's what those 3 dots mean in a triangular shape. Therefore, the particle is moving up. Okay, so that is what the particle is doing and the y. So we've given the actual explanation for it. All right, the second part says find the acceleration of the particle at time t equals 1.5. Is the velocity of the particle increasing at t equals 1.5, y or y not? Okay, so the first thing is finding the acceleration. Well, the acceleration is the derivative of velocity. So I'm going to say that the acceleration at 1.5 is going to be the derivative of velocity. Now, again, this was a calculator problem. You don't have to show this. All you have to do is write a of 1.5. Now, you can say over here, if you just want to be safe, a of t equals v prime of t, just to be safe. That's probably a good thing to write, to be honest with you. But the acceleration is the derivative, but we want it evaluated at 1.5. Guess what? We can use our calculator to do that if it's a calculator problem. Remember how I said that there was that n deriv thing? That is math 8. So if I push math 8, how about that? It's going to let me take a derivative. I want to do the derivative with respect to x, so I put that in there. Now I'm going to go ahead and type the function, which is going to be x sine of x squared. So x sine of x squared. And I want to do that when x specifically is equal to 1.5. Boom, there we go. That was pretty fast, actually. So it's negative 2.048. Negative 2.048. And again, there's no units. If there were units here, it would be meters or whatever the units are per time squared, whatever that is. Okay, so now what it wants to know is, because we found the acceleration, it wants to know whether the velocity of the particle is increasing at time t equals 1.5. Well, that means is the particle speeding up? Well, in order for something to be speeding up or slowing down, the velocity and the acceleration must be the same sign. Okay, and in this case, the velocity is positive while the acceleration is negative. So the particle is not increasing in its velocity. So we have to put that into words. So a of t, or a of 1.5, is less than 0. V of 1.5 is greater than 0. Therefore, particle is not speeding up. It's actually slowing down. So we've answered that question. All right. This last one is probably the most important of all of these, because you will see this in some form multiple times, and you're going to have to get used to what we're doing here. Number 19 says, given that y of t is the position function, is the position of the particle at time t, and that we know y of 0 equals 3, we want to know what y of 2 is. Okay, so this is the part that we have to understand. It's giving us some information about time t equals 0. It's giving us some information about time t equals 0. It wants to know information about time t equals 2. So we need to include 0 and 2 in our times somewhere. We know that a position function is an integral or an antiderivative of velocity. So really what we're going to do is we're going to say, okay, if I were to take the integral of the velocity function from 0 to 2 dt, that will give me my position function. Well, they've defined the position function here to be y of t. We're used to it being s for position, but in this case, they've called it y of t. So it's going to be y of t, that's the antiderivative of the velocity in this case, evaluated from 0 to 2. All right. So I know that the integral of the velocity from 0 to 2 is going to be y of 2 minus y of 0. And that's using the fundamental theorem part 1. I'm going to plug the 2 in for t, I'm going to plug the 0 in for t, and then I'm going to subtract. Well, the good news is I know one of those values. This is why we picked to use these specific values. Y of 0 is 3. I can find this integral because I'm allowed to use my calculator to do the integral from 0 to 2. And that's going to be the integral of this velocity function from 0 to 2. So let's go ahead and pull the calculator back out. We're going to do a math 9, which is the integral from 0 to 2 of x sine of x squared dx. And that's going to give us 0.826. And that's all we have to write, 0.826. So this is going to be 0.826. So now if I want to find y of 2, I'm just going to add 3 to the other side. So y of 2 is going to be approximately equal to 3.826. And that's the position of the particle at time 2. So really it's piecing all this stuff together. You're given 2 t values. You're going to use those in your integral when you have to use this fundamental theorem. You're going to do your antiderivative, which is what we did here. Do your fundamental theorem of calculus by plugging in the stuff. That way you're going to get the one that you have a given value for, and you're going to have the other one that you need to find the value for, and go from there. All right, last thing is we want to find the total distance traveled by the particle from 0 to 2. Well, really, it's exactly the same thing that we just did, except it's going to be the absolute value of velocity instead of just the velocity function that I plugged in. So we're just going to write that down because we know that's how you find the total distance, and then we're going to go back to our calculator. I wish there was a way to insert an absolute value around the x sine x squared, but I don't think that we can do that. So I'm just going to redo the whole thing. So math 9 0 2. So math num absolute value. You'll get used to this after a little while of using it. And then it's x sine x squared dx. And so the total distance traveled by this particle in the first 2 seconds is, drum roll please, 1.173. 1.173. And again, there would be units attached to this if they were there. All right, come back again with a separate video for each one of the other 2 pages, and that'll be it.